Okay, welcome to the hypothesis testing and p-values PowerPoint. We've hopefully solidified the z-score concept well enough that this will follow seamlessly, and you'll have the basis for all probability testing and statistics. So we've gotten through quite a lot of the class. We're doing p-values and hypothesis testing, and then we'll look at some of the particular tests in the next lecture that we use based on this method. So we now are getting into choosing what the right test is and what does a p-value mean after looking at normal versus non-normal data and how probability is generated. So far we've come up with scientific questions, we've written hypotheses, and now we're at the part of the course where we're going to learn how to test those hypotheses. So what's hypothesis testing? You were thinking, oh, well, so I'm trying to decide if my hypothesis is true or not. Well, really what we're doing is deciding whether there's a difference between the means of one group and another group. So when we're thinking about women smoking and not smoking versus lung capacity, we take the women in the smoking treatment group and the women in the control group, and we see what their lung capacity is and their mean lung capacity, and then we see if there's a difference between those two groups in their means. And what do we mean by difference is a mathematical concept of statistically significant difference based on probability. We'll look at that in a minute. You have to remember that there are two hypotheses. Neither of them are provable, both of them are falsifiable, and one says that there's not going to be any change or difference. The null hypothesis, or the H sub 0, let's highlight that, H sub 0, or HO, the null hypothesis is that there's no change. So if we think about women smoking and women not smoking, we'd say that the null hypothesis would be there will be no difference in the mean lung capacity of women who smoke versus women who don't smoke. And then we have the H1, or the alternative hypothesis. And this is really what we're testing, what we think about when we write an hypothesis. It says that there will be a difference between women lung capacity who smoke and who don't. This is what we're kind of thinking about when we start our experiment and what we're generally testing. And you'll see that those are opposites. They cover all contingencies. Either there is women who smoke have a higher lung capacity, or that they have a lower lung capacity. That's in the alternative hypothesis. And if they have the same capacity, then that is covered in the null hypothesis. So this is why we've done all of this work with the z-score table for the last little while. And we want to know whether something is significantly different, which is a mathematical concept. We don't use significant unless we're describing a statistical test, the output of a statistical test in science writing. And what we're doing, if you remember, is we're graphing the distribution of two groups and looking at their means. And if the mean of the second group falls somewhere on this line for the first group, which it will, then unless they're completely separated, then we can look at the probability by determining the area under this side of the curve using the z-score table, and where we can determine whether how unlikely it is that our mean would have fallen on this point of the line of the distribution if they weren't significantly different. If there was just by chance alone, we took a whole lot of individuals in our second sample that fell at the extremes of the distribution of the first group. So we can break this process down into 4 distinct steps. first, stating the null hypothesis and alternative hypothesis. We've had a little bit of practice at that, but you probably need a bit more, and that's what those hypothesis worksheets are for, and your workbook. Define the confidence required. So we decide whether we're going to have a 95% confidence level or an alpha of 0.05, or maybe 99%. We want to be 99% sure, or we'd have an alpha of 0.01, that there's a difference between the means. So we want to be sure that there's a 99% sure that there's a difference between the mean of the groups before we're happy to say that there definitely is. We want to be pretty sure before we make statements in science, because it's considered pretty bad form to write something and then get worked over by the reviewers or find out that you're wrong. But everybody is wrong sometimes. But this is why we use a pretty extreme confidence level in the sciences. In some sciences, like more qualitative sciences like sociology, they may use a p-level of 0.5. So they need only be 50% confidence before they start making conclusions about things. But in things like biological sciences, we tend to be at the 0.05 to 0.01. So then we're going to select and perform the appropriate statistical test. We've talked a bit about that. We're going to keep talking about that, which test to use with which variables. And we're going to make a decision, finally, about the validity of the null hypothesis, whether the groups are the same. When you're writing up your report, or when you're writing your hypotheses, you're going to state the null hypothesis first. And again, it assumes that there's no change or difference. So if we're looking at these particular forests, one is a regenerating forest here. Looks like it's all been clear cut, but it's ready to. It's got little saplings and things that are taking off. They're going to grow pretty fast, and then we've got this high biomass old growth forest, and we want to know whether this fast-growing forest A, it's quite a young forest, produces more leaf litter than forest B, okay, the old growth one. There's a lot of biomass and probably a lot of production in forest B, but maybe not as much production as this fast-growing stuff. We really don't know. Like this is, even though these things are growing faster, could they possibly keep up with the amount of biomass here? Anyway, so we're going to, the null hypothesis would be that the forest A has the same amount of leaf litter. And then the alternative hypothesis assumes that there is a difference, that forest A could be producing more or it could be producing less. But we're going to say forest A does not have the same amount of leaf litter as forest B. So that was writing our hypotheses, and now we're going to decide what confidence level to require. So the reason that we do this is because we can never be 100% sure. So we allow for a little uncertainty, and it will say that if we're 5% uncertain, we'll say that there's probably, and a pretty strong probability, that there's a difference in the means of the groups. In medical trials, that kind of thing, where you really want to be very certain, you will probably go to 1% or P equals 0.01. So P being probability. So this is called the alpha, what our probability is, or our confidence level. Okay, alpha, or the significance level. So if we are at a significance level of 0.05, that's a 95% probability that there's a difference between the means. And you are required to say what your alpha or your significance level or your confidence level is when you're doing your methods on your statistical analysis. Then the next step 3 is to select the appropriate test, and that depends on what type of data we have. Is it normal or not? So that'd be a normal distribution, and here's a right skewed distribution where the mean, median, and mode are not all the same. There we go. Where they are all the same in a normal distribution. Okay. Then it also depends on what type of data. Like if you have 2 continuous variables, then you're going to use a regression. But if it's not normal, then we go through a series of tests that are called non-parametric, and there'll be a different group of tests. We're not going to learn those in this course, but you should be aware that if your data is not normal, then you use equivalent non-parametric tests. Restating this, it's very important to choose the correct test. If you use the wrong test, you might wind up with thinking that your probability is 0.02, like that you're very sure that there's a difference between the means, but it might be 0.1 or 0.3 or something like that because you've chosen the wrong test, and then you report those results and then find out that you're wrong, you've overstated your conclusions, and that can cause a lot of grief. So as we said before, normal distribution, we do z-test, t-test, ANOVAs, correlation regression, like scatter plots with the line of best fit, like you saw, and non-normal, again, non-parametric equivalence, and then we get a p-value. So what is a p-value? So p stands for probability, and it's the probability that the results found happen by chance. Okay, the probability that there is not actually a difference in the means between the populations. So why p? P stands for probability, so you might get a p equals 0.6, something like that. So that would equate to 60%. Probability is 60%. But what we're testing is that the H sub 0, or that null hypothesis, that the results were not the result of a difference between the 2 populations, or that women smoking and women not smoking, that there was no difference based on their smoking in lung capacity. So you may find that the women who smoked did have a lower lung capacity than the women who did not smoke, and you're wondering whether it just happened because you chose a whole lot of women athletes or something in the women not smoking, and of course you'd expect that they'd have higher lung capacity. So what is the chance that just by picking individuals at the extremes that that was the cause of the difference seen? So we are testing with a p-value. The p-value tells us the probability that there is not a difference between the populations. So specifically, what does the p-value tell us in terms of a particular number? Remember, we're testing the null hypothesis. In the last example, the null hypothesis was that women who smoke will have the same lung capacity as women who don't smoke. There won't be a significant difference. All right, so what is a significant difference? With our alpha of 0.05, we want to be 95% confident that there is a difference based on smoking before we actually say it. So let's say a probability value of p.04, then there's only a 4% chance that there is no difference in the women's smoking lung capacity based on their smoking, and that means there's a 96% chance that there is a difference based on smoking. So we can be pretty confident, we can be 96% confident in this one, that there is a difference in lung capacity of women based on smoking. And so we can reject the null hypothesis because we're more than 95% sure of it. All right, so it could be that we just randomly selected samples who were at the extremes. Like, let's say we selected a whole lot of women who were competitive freedivers in the non-smoking group, and of course they're going to have a large lung capacity, and so whether there's a difference in lung capacity or not based on smoking, by choosing those extremes, you can falsely be confident that there was a difference when there's not. But that's why we go to such an extreme. That's why we go to such a high level of probability before we claim that there is a difference. Anyway, listen to Snoop. If the P is low, then the HO must go. Reject it. So if the p-value is lower, then the null hypothesis is rejected. Okay. But also, if the p-value is higher than 0.05, then we don't say that the null hypothesis is true. We don't say that there is definitely no effect of smoking. We just fail to reject the null hypothesis. So there's only a 15% chance that the results happen due to randomly selecting samples from the external. Or, said another way, we're 85% sure that the smoking may have had an effect on the lung capacity, but 85% is not confident enough to be able to say it. We've failed to reject the null hypothesis. It could still be true, but we've failed to reject it. So where's this p-value come from? We've kind of explained it with the overlap of the normal distributions, but we do it with a with a t-test in some cases, a statistical test on Excel or any other stats program, and we'll get this p-value generated in our output table. And so this 0.066, which would round up to 0.07, that would be too high to accept the null hypothesis, but they come from a stats test. So at this point, you can go to your workbook, answer the questions on p-values, and write down what does it show. Okay. So remember, when you're writing something down, instead of saying, if you've got this example with women's lung capacity, you don't say P is greater than alpha, so we will will fail to reject the null hypothesis. That doesn't say the same thing or as much to your reader as women. Let's say if P is greater than alpha, then you could say we did not find a statistically significant difference between women lung capacity in women who smoke versus don't smoke. That tells a lot more to the reader than just saying we failed to reject the null hypothesis. Then they have to go back and read and figure out what the null hypothesis was and all. We want to be very clear. Strive for clarity and trying to figure out, if you were reading this, how would I want to know, or how would I want this to be structured so that I could understand it very clearly if I didn't know anything about this information. And so, can a p-value get it wrong? Yes, it can. So that's why we always say that we're never proving anything in science. So there's a type 1 error, false positive, where you believe that there is a difference between two groups when there's not actually a difference, and a type 2 error when you believe there's not a difference between two groups when actually there is. So that would be the case where we got a 0.15 for the women smoking, and we failed to reject the null hypothesis. We concluded that we said that we couldn't conclude that that smoking had an effect on lung capacity, when in fact it does. And these two slides just reiterate what we were just saying. If you need to stop the video and look these over, take the time to do that. That's fine. Okay, so that's the end of what probability testing or hypothesis testing is and what a p-value is. In the next video, we're going to look at a specific test called a t-test.